Good morning, everyone. I'm Xian, and I'll be presenting on my final year project, which is on peer-to-peer cluster federated learning, specifically on establishing cluster formation criteria via the Gale-Shapley algorithm to match nodes to clusters. First of all, what is federated learning? Federated learning is a machine learning technique that allows models to be trained across decentralized devices or nodes. It eliminates the need for raw data to be centrally collected in one location. Instead, the model is trained in a distributed manner across multiple nodes. Each node only sends model updates and not the raw data to a central server. This technique is useful when data privacy concerns or bandwidth limitations make centralized training infeasible. Fed-average is a popular federated learning algorithm used to train machine learning models on decentralized devices. It involves dividing the participating devices into groups, and each group is assigned a unique set of tasks. Each client device trains the shared global model using its own local data set and sends the model updates to a central server. The server then aggregates the model updates by taking the average of the model parameters to compute a new global model, which is then sent back to the clients for further training. This process is repeated iteratively until the model converges, resulting in a model that is trained on a large number of decentralized client devices while keeping the raw data on those devices private. The Fed-average algorithm has been shown to be effective in various applications, including natural language processing, computer vision, and speech recognition. Peer-to-peer Fed-average is similar to normal Fed-average, but done in a peer-to-peer manner. The nodes will first have to form clusters, and within each cluster, the nodes communicate with their immediate neighbors instead of with a central leader node. Each node keeps track of both a global model and its own local model. The leader node is selected and trained on its own local model and serves as the initial global model. This leader node then sends its global and local model updates to neighbors. The neighbors then use the global model weights to train their own local model using their own local data set. And then the neighbors will send their local model updates as well as the global model weights to the corresponding neighbors. And this whole process continues until all nodes have participated and returned to leader node. The leader node then averages all local model weights to update the global model. And this process repeats until the model converges to a certain level of accuracy or until the end of all communication routes. For efficiency, the shortest path between all nodes are always taken. Within each cluster, every node must be reachable from every other node. In a multi-node, multi-cluster situation, a new node can request to join any of the existing clusters in order to participate in the training process. This decision of which cluster should the node join is actually quite complex. A node may want to join a cluster that is physically closer to because it has limited communication bandwidth. It may also want to join a cluster that's further away simply because that cluster has a higher model accuracy or a similar objective that the node also wants to accomplish. Hence, there are many factors to be considered before the node can make a decision on which cluster to join. Some of these considerations include proximity. The node may prefer to join a cluster that is physically closer to it, as this can reduce communication latency and improve overall model performance. Similarity of data distribution. The node may prefer to join a cluster whose clients have similar data distributions to its own, as this can improve model accuracy and convergence speed. Cluster size. The node may prefer to join a cluster that has an ideal number of clients, as this can help ensure that its contributions are balanced with those of other clients. Cluster representative. The node may prefer to join a cluster whose representative it trusts or whose selection process it understands, as this can affect how its model updates are aggregated and ultimately affect the final model quality. Network latency. The node may prefer to join a cluster with low network latency, as this can reduce communication overhead and improve overall performance. Security and privacy. The node may prefer to join a cluster that has strong security and privacy measures in place to protect its data and model updates. Availability of resources. The node may prefer to join a cluster that has adequate computational and communication resources to support its training process. Reward level. The node may consider what kind of reward that it can derive by joining the cluster, such as higher model accuracy or priority to get picked to join the next training process. Objective of cluster. Different clusters may have different training objectives. Accuracy might not be the concern of the node, and hence, a node may choose to join a cluster with a training objective that better aligns with its own. Personal preferences. The node may also have personal preferences or prior experience with certain clusters or clients that influence its decision to join a particular cluster. Similarly, when a cluster is formed and a new node requests to join the cluster may decide whether or not to accept this new node. Some of the cluster's considerations include available resources. The cluster may consider whether it has adequate computational and communication resources to support the new node's participation in the training process. If the cluster is already resource constrained, it may not be able to accept additional nodes without negatively impacting performance. Data distribution. The cluster may consider whether the new node's data distribution is similar to that of existing nodes in the cluster. If the new node's data is significantly different, it may not contribute effectively to the shared machine learning model. Contribution potential. The cluster may consider the potential contribution that the new node can make to the shared machine learning model. If the new node has high-quality data or strong computational resources, it may be a valuable addition to the cluster. Even if it does not have high-quality data, the addition of the node can reduce shortest path length. This node may still be considered valuable to the cluster. Trustworthiness. The cluster may consider the trustworthiness of the new node, particularly with respect to security and privacy. If the new node has a history of security breaches or has not demonstrated a commitment to protecting its data, the cluster may be reluctant to accept it. Alignment with cluster goals. The cluster may consider whether the new node is aligned with its goals for the training process. For example, if the cluster is focused on developing a model for a particular use case, it may prefer to accept nodes that have data relevant to that use case. Network latency. The cluster may consider the network latency between the new node and existing nodes in the cluster. If the new node is geographically distant or has a poor network connection, it may negatively impact communication and performance. Cluster size. The cluster may consider whether the addition of the new node will result in an unbalanced distribution of clients or create other logistical challenges. Prior experience. The cluster may consider its prior experience with the new node, such as whether it has collaborated effectively in the past or has a reputation for being difficult to work with. Other constraints. The cluster may consider any other constraints or requirements that it has for accepting new nodes, such as legal or regulatory considerations. As you can see, this sounds very similar to the stable marriage problem, which is a problem that involves finding a stable matching between two sets of entities, where each entity in one set has a preference list of entities in the other set. For instance, you can think of this as matching student applicants to various universities. And this problem can be solved by the Gale-Shapley algorithm. The algorithm begins with each entity proposing to their most preferred partner. Each entity either accepts or rejects the proposal based on their own preferences. If an entity is rejected by their preferred partner, they'll propose to their next preferred partner and continue until they are either accepted or they run out of potential partners. This algorithm continues until a stable matching is found. And this algorithm is guaranteed to produce stable matches because if an entity is rejected, they'll move on to their next preferred partner. And the algorithm continues until each entity is matched with a partner. The algorithm will then check whether the matching is stable or not. If it's not stable, the algorithm will repeat the entire process with the entity that broke the stability condition by proposing to their next preferred partner. And this iterative process will continue until a stable matching is found, ensuring that no entity has an incentive to break the matching. We ran a few experiments and arrived at these following conclusions. Clustering improves model accuracy, and when considering whether to accept a node into a cluster, we have to consider all factors together instead of considering only one or two factors. And the Gale-Shapley algorithm has proven useful in producing stable matches that result in overall higher model accuracy. Thank you.